Last lecture, for gases, we left off with this example of Boyle's law. Boyle's law is one of our simple gas laws. There are several simple gas laws. Boyle's is just the first of them. Boyle's law relates pressure and volume. P1V1 equals P2V2. So in one state with a pressure value and a volume value, if you change the pressure, the volume will change, or if you change the volume, the pressure will change. And if you multiply those two values, they'll be the same. So we looked at how to do a very simple rearrangement of P1V1 equals P2V2 in order to get a solution, in this case, solving for V2. If I'm remembering correctly, we've got we've got at least three other simple gas laws that we'll learn that relate different things. So Boyle's law is pressure and volume. Charles' law is volume and temperature. So you may know that hot air rises, but you may not know why hot air rises. So hot air balloons float. It's not by magic, although it looks like magic. And navigating in a hot air balloon still, to me, feels like magic, even though I know how they float. So the reason that hot air rises, it turns out if you heat a gas, that increases the volume. So heating a gas increases the volume. If you raise the temperature, you raise the volume, but mass doesn't change. So if we look at density, if we make volume bigger, we make our volume bigger and our mass is constant, our density will decrease. We're basically just spreading out all of those particles so that they take up more space, and that causes the density to go down. And like we learned and used in one of our early labs, low density floats on high density. This works for gases like it does for liquids. It's like if you jump in a pool, lots of us probably float in the pool because we're less dense than the water. Some of us maybe sink in the pool. Some of us, it maybe depends on whether we've got air in our lungs or not. Gases, it's the same thing. We just don't see it very much. You will see this happen maybe a little bit if you're looking at really big temperature differences. So like if you're looking at really hot surfaces, sometimes you'll be able to see like the air kind of wiggling and shimmering, and that could be related to this property. I think there's some other things going on in there as well. This temperature difference is also the reason why, if you've ever lived in a two-story house, the hot air will find its way up to the top story, the second floor, and the cold air will tend to settle on the first floor. So volume increases with temperature. If you plot temperature on an x-axis and volume on a y-axis for any gas, you'll find this linear relationship. So as you increase temperature, volume also increases. And they're directly proportional to each other. If you predict this line backwards, you can find the point where it intersects. And with temperature in Kelvin, that temperature is 0 Kelvin. So at 0 Kelvin, a volume of nearly 0 is expected. The reason that it's not actually 0 is because the particles still take up some space. So it can't actually be 0. It can't fold in on itself and disappear. Or at least I assume that it can't. Nobody's hit absolute 0 yet. You can't have negative volume also. Hopefully that also makes sense. And this 0 point the minimum volume, that temperature is what we call absolute zero, which is where 0 Kelvin is set. They've gotten really close to 0 Kelvin, like I think it might be nano or picokelvin. So they've gotten really, really close to 0 Kelvin, and things get really funky when you get close to there, so that's maybe a fun look. Look at what happens when you get close to 0 Kelvin. It's really weird. So that's where our 0 Kelvin comes from, and our Kelvin scale is based off of that. J.A.C. Charles, who's French, was French, quantified the relationship between volume and temperature. So volume of gas and temperature, the assumptions that we're making with Charles' law is that we have constant pressure and we have a constant amount of gas. So the way that the hot air balloon works, it heats up the air in the giant balloon, and that balloon has to be open to the environment so that some of the air can escape, and then you basically have a big, really low density air bubble, and it just kind of floats up in the rest of the air around it. And then they can also like release some of the hot air if they want to go down, or heat it up more if they want to go up more. Just because I forgot to talk about it on that slide. Okay, so our relationship, volume and temperature are directly proportional, and we saw earlier proportional just means equals times some constant, so we can turn that into this V1 over T1 equals V2 over T2. So if you wanted to memorize Charles' law, this is the law that you would, or the formula that you would probably want to memorize. A takeaway from this is that when the temperature of a gas in kelvins is doubled, its volume also doubles. In order for this to work, temperature must be expressed in Kelvin. Notice that this line is italicized and there's an exclamation point, and I also underlined it. Even the previous sentence says that it needs to be in kelvins. The reason for that is if we don't have it in kelvins, if we go back to our plot, if we don't have it in Kelvin, if we had it in Celsius, for example, then we'd have a line. Our y-axis would be somewhere along this red line, and it wouldn't intercept at 0. And so for our equation y equals mx plus b for a linear graph, we would have a y-intercept term of b, and we don't know what that value is. So the calculation doesn't work. This is a mistake that some of you are probably going to make. It has to be Kelvin for Charles' law to work because it hinges on the fact that temperature and volume are both 0 at the same time, or as close to 0 as they can be. So instead of being this y equals mx plus b, it's just y equals mx, which looks an awful lot like v equals kt, which we could rearrange into v over t equals k, which would also be equal to v over t in some other state. And would you look at that? It's Charles' law. We can't do that if we've got a plus b term in there. You're welcome to try it. It won't work out unless you know what b is. Then you can do it. So it has to be in Kelvin. Anytime we're working with gases, your temperature needs to be in Kelvin. From kinetic molecular theory, the way that this connects, if the temperature of a gas sample is increased, the gas particles move faster. For the pressure to remain constant, the volume has to increase. So because they're moving faster, they're going to bump into each other more. They're going to tend to want to spread out so that they bump into each other less. If they bump into each other more, that would increase the pressure. But because the pressure around them doesn't have that increase, they're going to push out from that pressure area. Here's how you can appreciate Charles' law at home. This is relatively safe as long as you're not scared by really loud noises. if you blow up a balloon, don't blow it up all the way. Blow it up like maybe half of the way. If you blow it up all the way, it might pop. You can take that balloon and put it into some cold water, some ice water, and the temperature will drop. The volume of the balloon will also go down because the outside pressure is the same. It's equal to the inside pressure. That's how it's inflated that size. So it'll shrink when you put it into the cold water. And then you can run it under some warm or hot water and you'll be able to watch the balloon or blow up a little bit. And hopefully it doesn't pop. So that's something that you could try at home if you wanted like a visual watching Charles' Law work. Another takeaway that I've used, because I know that heat rises and cold air falls, since hot air rises, sometimes, not usually during class or when I'm teaching, sometimes when I'm warm, I'll just pull the neck of my shirt out. You might have seen kind of people flap their collar of their shirt. If you do that, the hot air has a nice place to escape. If you're wearing a shirt that's not tucked in, you can pull the bottom out too. It makes a nice little column for all that hot air to escape and cool you down a little bit faster. So that's something that you might try maybe in the privacy of your own home and then figure out if you like it. All that being said, those are just kind of some fun takeaways. We want to see, what does Charles' Law look like in practice? Again, like with Boyle's Law, one of our big things that we want to make sure we do is get our state 1 and our state 2 lined up. So we want to make sure that the volumes and temperatures that go together stay together, then we don't get them mixed up, because we will get the wrong answer if we do that. So we've got a balloon. A balloon is filled to a volume of 2.20 liters at a temperature of 22 degrees Celsius. The balloon is then heated to a temperature of 71 degrees Celsius. Find the new volume of the balloon. So just like before, we've got a couple of variables. We'd have to have 3 variables. We've got a volume that's equal to 2.20 liters. We've got a temperature of 22 degrees Celsius. We've got another temperature of 71 degrees Celsius. Please, in your brain, identify which of these temperatures goes with our volume. All right, which of these temperatures goes with our volume? 22 degrees Celsius. We know that it's 22 degrees Celsius. They're in the same sentence. So that's going to be, let's call that state 1. And then we'll call this 71 degrees Celsius our state 2. And that would make our new volume also state 2. So we're trying to find V2. We've got our V1, our T1, and our T2. Again, if you get them switched, you will get the wrong answer 100% of the time. All right, we're solving for V2. V2 is on the top, on the right side of our Charles' Law. We need to get it by itself. It's already in the top, but we need to get it by itself. To get it by itself, we need to move our T2 to the other side. So our equation will be V2 equals V1 over T1 times T2. You may have noticed on our Boyle's Law that we had one variable on top and the same variable in the other state on the bottom. We have that here again. So in this case, we've got T2 on top and T1 on the bottom. It's important that we have T2 on top and T1 on the bottom, or vice versa, depending on the situation. But we have to have the same variable on the top and the bottom, the one that we're not finding, in order for those units to cancel each other out. Otherwise, our units won't make any sense. So this is a check that we can run through to make sure we didn't screw up the algebra. All right, and then we plug in. V1 is 2.20 liters. T2 is 71 degrees Celsius. And T1 is 22 degrees Celsius. You can see that our degrees Celsius will cancel. So 2.2 times 71 divided by 22. With this, we get a value of 7.1, and our units of liters follow through. This is not the right answer. But if this were an exam, this would be one of the answers, one of the possible choices. Why is this not the right answer? Yeah, we use degrees Celsius. What units do we have to use? Kelvin. So this whole thing is wrong. Needs to be in Kelvin. So we'll convert both of our temperatures to Kelvin. To do that, we add 273.15 V2 equals, V1 is still 2.20 liters. The volume units don't matter. And we're multiplying that by 344.15 Kelvin. And we're dividing that by 295.15 Kelvin. The Kelvins cancel. And this will be equal to, let's find out, 2.57 liters. So instead of more than tripling in size, because it would have gone from 2.2 liters to 7.1 liters, that's more than triple the size, it just gained a little bit. So from 2.20 to 2.57. It didn't even double. Less than 50% increase. Questions? Okay. Now one for you to do. Gas in a cylinder with a movable piston has an initial volume of 45.8 milliliters and is heated from 25 Celsius to 100 Celsius. What's the final volume of the gas in milliliters? In this case, it does matter what units we use for our final volume because it asks specifically for milliliters. I'll give you a couple minutes to work on this one. And I guess I'll give you Charles' law too. All right, for the people in the room, that was about 3 minutes. So we've got a Charles' law problem. We've got some values. We've got an initial volume of 45.8 milliliters, and it looks like I missed a space before 45.8 milliliters, so that's fun. So V1, because that's our initial state. Usually people like 1 to be the initial state. 45.8 ml. It's heated from 25 degrees Celsius to 100 degrees Celsius. So we've got some temperature values. 25 C and 100 C. Let's just assume that it's 100 degrees Celsius. Which of those temperatures is our initial value? So 25 degrees Celsius, because it says from 25 degrees Celsius, so that's where we started. So this is our T1, and 100 degrees Celsius is our T2. What should we do right now? Convert it to Kelvin. Right now, before we even start rearranging our equation, our temperature needs to be in Kelvin, or we will get the wrong answer. It'll look like our volume quadruples if we don't. So we would get a value of 183.2 or something like that, milliliters. If you got a value of 132.8, whatever I said, you forgot to convert your units. So we want to add 273.15. And these turn into 298.15 Kelvin and 373.15 Kelvin. These should both be 3 significant figures based on our initial temperature values. And then we are solving for V2. This is going to give us the same solution that we used in the previous problem. V1 T2 over T1. So our V1, 45.8 ml multiplied by T2 in Kelvin divided by 298.15 Kelvin. Put it into the calculator. And we get a value of 57.3. 57.3 milliliters. Questions? All right, so that's Charles' law. If you loved Boyle's law and you love Charles' law, don't worry, we can put them together, and you're going to love the combined gas law because it's both. So Boyle's law and Charles' law can get put together. We call this the combined gas law. I guess you could probably also combine some of the other gas laws, but this is the one that we call the combined gas law for some reason. So if we're changing 2 variables at once, then we might want to use Charles or the combined gas law. With the combined gas law, the amount of gas is constant, and look at that, temperatures in kelvins. Another situation where if your temperature is not in kelvins, it will be wrong. You can make the combined gas law if you remember Boyle's law and Charles' law. Boyle's law is P1 V1 equals P2 V2. Charles' law is V1 over T1 equals V2 over T2. And all that we're doing to get the combined gas law is we are combining these 2 laws. I mean, that's like what the name says. I didn't do a very good job of it, but look at that. If we overlap, if I did it in different colors, it would look better. But if we overlap our V1s and our T2s, sorry, our V1s and our V2s, that's the combined gas law. Or if I was typing, I guess that would also work. So we combine them and the V's overlap. So our combined gas law, if you thought 3 variables was fun, now we've got 5. For our combined gas law, P1 V1 over T1 equals P2 V2 over T2. So gases is like the opposite of the chapter that we were in previously. The previous chapter was like all concepts, and this is like maximizing our algebra value. We're like algebra maxing when we're talking about gas law stuff. So a sample of gas has an initial, keyword initial, volume of 241 milliliters at a pressure of 755 mmHg and a temperature of 32 degrees Celsius. So that's all of our initial states. We'll call that 1. So V1, P1, and T1. V1 of 241 ml, pressure of 755 mmHg, and a temperature of 32 degrees Celsius. Next sentence. If the gas is compressed to, we're doing an action to get to a second state, compressed to a volume of 115 milliliters and heated, changing the temperature, to a temperature of 94 degrees Celsius, what, question word, is its final pressure specifically in millimeters of mercury, which is mmHg? So we've got our V2 given to us 115 milliliters, and our T2 is 94 degrees Celsius. We're asked to find pressure. So we're looking for P2. We could, if we really wanted to, make a prediction before we put any numbers into our calculator about whether our P2 is going to be higher or lower than our initial P2 or P1. If we look at volume, our initial volume is 241 milliliters. Our final volume, or our second volume, is 115 milliliters. So we've compressed it. How would we expect that to change pressure? Is pressure going to increase or decrease? Yeah, if we decrease volume, we expect our pressure to increase. And we also heated it. So we heated up the gas that was in this container. The volume can't expand, so how do we expect that increasing the temperature will affect our pressure? Is pressure going to increase? Is it going to decrease? What would the gas like to do when we heat it up? It would like to expand. We've constrained the volume. It can't expand. So what's that going to do to the pressure? Is it going to increase or is it going to decrease? It's going to increase. So based on both of the things that we're changing, both of them say that pressure is going to increase, so we would expect our pressure overall to increase, and possibly by quite a bit. The other thing that you can think of with the the temperature change. If you have a water bottle, most of us have a water bottle or have had a water bottle, you fill it up with water at home, you go out and do some errands, or you're out in the sun, and then you open it up and it's heated up, it's no longer ice water. You can hear the pressure escaping when you open it up. That's because the pressure is built up inside from that temperature increase. And then you open the lid and you can hear it whooshing out. All right, so to solve for P2, we need to identify P2. There it is. In our combined gas law, we need P2 by itself. So to get P2 by itself, we need to move V2 and T2. So we have to multiply by the inverse on both sides. So we've got T2 on the bottom on the right side. We need to multiply by it, so those cancel. We've got V2 on the right side up in the top, so we need to divide by V2 on the right side so that it cancels. So that will leave us with T2 over V2 times P1 V1 over T1. There's something we forgot to do. What did we forget to do? Convert to Kelvin. We didn't convert our temperatures to kelvins. So add 273.15 kelvins to each of those. So T2, 94 plus 273.15. This is 367.15. Now in units Kelvin. Our P1, 755 mmHg. And our V1, 241 ml. On the bottom, we've got our V2, 115 ml, times T1, 305.15 Kelvin. Any questions about the setup? All right, our units, just checking our units. We've got Kelvin on the top and on the bottom, those cancel. We've got mLs, milliliters, on the top and the bottom, so those cancel. And we'll be left with units of millimeters mercury. That's what we wanted. So now we just have to plug this whole thing into our calculator. So multiply everything on the top and then divide by the things that are on the bottom. So 367.15 times 755 times 241. And then you can divide by sign and start a parentheses and then type this bottom part in. Or you can divide by 115, hit divide again, 305.15. Either way, you'll get the right answer. And you should get a value of around 1,904 millimeters of mercury. So 1.90 times 10 to the 3 millimeters of mercury would be our final answer. We had previously predicted that the pressure would go up. We were right. Or at least this is consistent with what we predicted. If we had gotten a value that was smaller, then that might be a warning sign to us that we did something wrong. We also have another simple gas law, Avogadro's law. Avogadro is famous for a number. What's that number related to? Atoms, or formula units, or molecules. And what's the other part? What's the other unit? Moles. So Avogadro's number is the number of particles, the number of pieces in 1 mole of whatever that thing is. So that might be helpful for connecting Avogadro's law, the name of the law. We know that there's going to be moles in there. Moles gets the symbol of lowercase n. So what happens if the amount of gas changes? So if we add gas or if we remove gas. What we can do is measure the volume of a gas at constant temperature and pressure and vary the number of moles in the sample. And believe it or not, this is probably something that all of you have done. You just didn't record data about it. So the volume of a gas sample increases linearly, they're proportional, with the number of moles in the sample. We'll see an example of this on the next slide. This was first formally stated, the first recorded or recognized statement was by Amedeo Avogadro, same guy that has that number. It assumes constant temperature and pressure. So Avogadro's law, V is proportional to N. And so we end up with V1 over N1 equals V2 over N2. Basically, this states when N increases, N being the number of moles, volume increases. When the number of moles of gas decreases, volume also decreases. So they both move. If one moves in one direction, the other moves in the same direction because they're directly proportional. Inversely proportional is when the directions are opposites. So here's the example that probably all of you have experienced. You've at least seen it. It's blowing up a balloon. When you're blowing up a balloon, the pressure around us here is about 1 atmosphere. That's constant. You're not changing that by blowing air into a balloon. The temperature doesn't change significantly. So you blow some air into a balloon. When you're blowing air in, you're adding air, you're adding moles, and the balloon inflates. This is all that Avogadro's law is telling us. When you blow up a balloon, it gets bigger. If you release some of the air, it gets smaller. Most of these laws feel serious, and then they're just so simple. All right, V1 over N1. A balloon, to do an example, a balloon has been filled to a volume of 1.90 liters with 0.0920 moles of helium gas. If 0.0210 moles of additional helium is added to the balloon while the temperature and pressure are held constant, what is the new volume of the balloon? What are we finding? Yeah, we're finding a volume. We would probably call this V2. And what are we given? What information are we given? V1, 1.90 liters. And we have to have the other two variables, which is N1 and N2. I very helpfully wrote 1 on both sides. It's true, it's just not helpful. So N1 is what? It's our first number of moles. 0.0920 moles heat. And what's N2? Yeah, let's put down 0.0210. Sorry, 0.0210 moles, also He for helium. Okay, let's solve for V2 because that's what we're being asked to find. So V2, it's already in the numerator, it's on the top. It's not by itself, so we haven't solved for it yet. We need to move N2. So multiply by N2 on both sides so that it cancels out on the side that has V2. If we flip it left and right and change some colors, V2 equals N2 times V1. We can put that all over N1. What do we expect for our answer? Do we expect our volume to be bigger or smaller? Before you calculate it, do we expect our volume to go up or go down? We expect our volume to go up, says one of our classmates. Does anyone disagree? Okay, we expect V to increase, right? We're adding helium. Let's do our calculations. So equals, we said that N2 is 0.0210 moles helium. And V1, we said was 1.90 liters. And N1, we said was 0.0920 moles helium. The identity of the gas doesn't actually matter. That's part of our kinetic molecular theory. It's related to it at least. The unit that we'll have left over is liters. Let's put it in our calculator. 0.021 times 1.9 divided by 0.092. Get a value of 434 liters. Did our volume increase? According to our calculations, volume decreased. So either our expectation was wrong or our calculation was wrong. Who knows which one it was? Any ideas? Our expectation was correct. Our volume should have increased, right? Because it says that we added additional helium. N is the amount of gas in the thing. So we missed a key word when we were putting this problem together. This is 0.021 moles of additional helium. So we're adding helium. Did we have helium in the balloon already? Yes, we had some helium in the balloon already. So the amount of helium that we had in the balloon was that 0.0920 moles. And then we added 0.0210 moles. So what would our N2 be? It would be the initial plus the amount that we added. So that's where we went wrong. Are we seeing that? So plus 0.0920 moles of helium. So our N2 is actually 0.113 moles of helium. So if we repeat the calculation, but with the correct N2, (0.113) moles of helium. We get 2.33 liters. Which is bigger than the 1.90 liters we started with. So we're not taking crazy pills. We just missed some words. Questions? I think problems like this are fun. Students disagree, in my experience. My gut tells me I've probably put one question like that on exam 3 historically. Maybe 2, because it's fun. And some of you also probably find it fun, but it's just like one of you. And the rest of you are going to be mad at me. That's fine. All right, let's try Avogadro's law, or give you a chance to find Avogadro's law answers. V1 over N1 equals V2 over N2. We have a reaction vessel, just a container for doing a reaction. It's got a movable piston, so the volume can change. It's filled with 0.121 moles of reactant A, 0.452 moles of reactant B. The initial volume of the vessel is given, 1.53 liters. After the reaction is complete, keywords, the volume of the vessel is 0.884 liters. How many moles are present in the reaction vessel? This is also a fun problem. I'm going to echo the words that I said on the previous slide. The identity of the gas does not matter. I'll give you some time to let your brains work on this one. All right, let's make a prediction. I know some of you may not be quite done yet, but just based on the thing that's changing, let's make a prediction about our answer. The thing that we've got both of, the one variable that we've got both values for is volume. We've got initial volume, 1.53 liters. And we've got a V2, 0.884 liters. Based on our volume, and maybe thinking about a balloon, do we expect our number of moles to go up or down? What's our volume doing? Is our volume going up or going down? Our volume is going down. What do you need to do to a balloon in order for it to get smaller? you have to put more air in? Do you have to take air out? You'd have to take air out. So we expect our number of moles to decrease. So volume got smaller. So we expect N, number of moles, to get smaller or to decrease. What are we using for N1? Are we using 0.121 moles or 0.452 moles? The correct answer is no. We're using them combined. We have to add them together. So the total amount of moles of gas that we have in our container is the moles of A plus the moles of B. I said earlier the identity doesn't matter. So N1 is the total number of moles regardless of what type of chemical they are. So 0.121 moles plus 0.452 moles. So 0.573 moles. That's what I would consider the trick, with air quotes. It's sort of a trick. The problem-solving fun of the question. I'll give you some more time in case you were stuck on that to try to finish the problem. All right, so we're solving for N2. That means in our equation, we need N2 to be by itself and on top. Whatever we're solving for must be by itself, needs that side of the equation, that side of the equals to be only that thing, and in the numerator on top. So if you got a value of about 3, you missed one of those 2 points. You got it by itself, but you didn't get it in the numerator, you had it in the denominator. One of the things that we can do with Avogadro's law, we can do this with any of the gas laws, this is just the first time that we're seeing this happen. We're trying to find something that's in the denominator. It would be easier for us if we didn't have to switch everything around. So normally the way we would get N2 by itself, we'd multiply by N2 to move it from the right to the left, and then we would have to move V1 and N1 over to the right side. And we can do that. So that looks like this whole mess. Nope, I did the wrong thing. Correcting. N1 over V1. So we would end up with N2 equals V2 N1 over V1. We can do that. However, we can save ourselves some steps. At any point in time, for any equation ever, you can always, for free, with little brain power involved, flip the top and the bottom. Anything that's on the top, everything that's on the top, put it on the bottom, everything that's on the bottom, put it on the top instead. This is one of those times where this could be helpful. So starting with V1 over N1 equals V2 over N2. To get N2 to the top, we're going to just flip the whole thing. For a lot of equations, this is not a helpful trick to have in our basket or in our toolbox. For this one, it is. The reason this is helpful is that now N2 is by itself in the numerator. To get rid of V2, we just multiply both sides by V2. You can, of course, do it the other way. If we look at this flipped version, N2 equals V2 N1 over V1. That's the same as what we got with doing the extra step. The way that I did it, the long way. They're about the same, but the quote-unquote long way. So N2 equals V2, which is 0.884 liters, times N1, 0.573 mole, over volume 1, 1.53 liters. Liters cancel. We're left with moles. Put it in the calculator. We get 0.331 moles. That is smaller than our initial moles, so that fits with what we expected. We let air out of the balloon. Questions about that problem? This is also what I would consider a fun problem. Students disagree. Similar to the previous fun problem, again, expect only 1 or 2 fun problems on the exam. This is, believe it or not all of the simple gas laws. We've looked at 4. We looked at Boyle's law. We looked at Charles' law. We put them together, and we got the combined gas law and finally Avogadro's law. There's also the Gay-Lussac law, which we don't go over just because it's not in my slides and I don't feel like adding it. And if that feels like a lot of laws to memorize, a lot of simple equations to memorize, there is a shortcut. You just have to be able to do algebra and remember the trick. And that shortcut is by using the ideal gas law. The ideal gas law combines all of our simple gas laws. Our ideal gas law is usually written in the form PV equals nRT. This can be rearranged. This is just the way that we normally write it because everything's on top, which is super helpful for us because then when we want to find any of those variables, we just divide by everything else on that side on both sides, and now we've got our answer. We don't have to do any of the flip top and bottom or extra algebra steps. So we use PV equals nRT because we don't have to do any of that. It also fits in one line. It's easier to write in the slides. So the things that we have seen before, right? We've seen pressure. We know P, P's pressure. We know V, that's volume. We know that N is moles. We know that T is temperature. R is new. R is the ideal gas constant. Ideal gas constant. Someday I'll stop skipping the first letter or number of things that I'm trying to write. I've been saying this for years. Today is not that day. R is this number. This is one version of R. There are other versions of R. There's also a version where it's 8206 instead of 821. You can also change the units. This is the one that we'll most often see. So R is 0.0821 liters times atmospheres over moles times Kelvin. Having R does some helpful things for us. If we're given R, it has to have units given with it. And what this tells us is the units that we have to use for P, V, N, and T. N's always going to be moles. but the rest of them we're reminded. So pressure has to be in atmospheres, volume has to be in liters, and temperature has to be in kelvins. That's also described here in the bottom half of this slide. Another thing that you can do with R is, if you're decent at algebra or good at algebra and you know what unit you're trying to find, you can just figure out based on the units of R what you need to do to solve it. It's like if I needed to get atmospheres is on the top, I would need to get rid of liters, moles, and Kelvin. So I'd multiply by moles and Kelvin, and I would divide by liters. That would leave me with atmospheres. So if you completely forget the ideal gas law, that would be one way to solve ideal gas law problems. Just with R, I don't expect you to do that. But it could be done. The ideal gas constant, or the ideal gas law, is really cool because we can make all of the other gas laws from it. It also, notice that there's no ones or twos. We don't need a reference state. So we don't need to know the variables in one state. We just need to know one set of conditions and we can find the last variable. We don't need to change a system from one state to another state and then we can figure it out. Just one set of conditions, we can find whatever we want. Showing us how we can find the other gas laws. If we have a problem with pressure and temperature changing, so where we are going to have a P1, a P2, a T2, a P2, for example. This is one that we haven't looked at. This is what would be Gay-Lussac's law. What we're going to do is rearrange PV equals nRT so that P and T are on the same side. So P over T equals nR over V. We divided both sides by TV, which gets the V to cancel on the left side, it gets the T to cancel on the right side. So now we've got the two things that we care about over on the same side, P over T. We can copy paste that. Number of moles, the gas constant, and volume would all be constant. So that we can just turn it into a constant. P over T, call it P1 over T1 equals P2 over T2. Copy paste it. And we would get Gay-Lussac's law. This will also work for any of the other gas laws. So the things that we're changing, the variables that we have for any of these simple gas law problems, put those on one side, add ones underneath them, copy paste it, change the ones to twos. So starting with PV equals nRT. Avogadro's law is the number of moles and the volume. So let's say we've got an Avogadro's law problem. We know that we've got number of moles and volume. We don't remember how they're related to each other. So we want to find the N and V relationship law. We need to get V and N on the same side. So divide both sides by N to move the N to the left side. PV over N equals RT. We also have P over here. We don't want P over here. Divide both sides by P to cancel P out, and we get V over N equals RT over P. So we've got V and N together. Ignore the other stuff. Rewrite V and N, add ones and twos. V1 over N1 equals V2 over N2. That's Avogadro's law. So if you like this, if this makes sense to you, you don't have to memorize the simple gas laws as long as you know what variables you're working with. I think in the past, though, I have put Boyle's law. I've asked which of these is Boyle's law. You can also figure that out because it'll show you that it's pressure and volume related to each other in some way. You just have to figure out how you manipulate PV equals nRT to get Boyle's law, the thing that has P and V in it. Which of those can you make from the ideal gas law? Questions about that? Again, if it doesn't make sense to you, forget about it. If it doesn't seem like it's going to be helpful for you, it's just an extra tool. I think it's really neat. If it doesn't work for you, don't worry about it. You can just memorize the simple gas laws. All right, let's show the power of the ideal gas law. Let's use it. PV equals nRT. We've got a question. What is the volume? So we're finding the volume. So finding V, we're given 0.453 moles of gas, the temperature 473 Kelvin, and the pressure is 2.7 atmospheres. We would look up or have memorized R value. R equals 0.0821 liters atmospheres over moles Kelvin. Please continue to be diligent in writing out all of your units all of the time. Or if you haven't been diligent about writing all of your units out all of the time, start. So we're solving for V. We need to rearrange this so that V is by itself. What are we going to move? What variable do we need to move to get volume V by itself? Pressure, P is the same on the same side, and we need volume by itself. So volume equals nRT over P. Our shortcut, if it's on the top, we can move it to the bottom of the other side. If it's on the bottom, we can move it to the top on the other side. In this case, pressure's on the top, move it to the bottom of the other side. That's the end result of dividing both sides by P. So V equals nRT over P. Notice that we've just got one value for each of N, T, and P. We don't need a reference state. So N, 0.453 moles. R, 0.0821 liters times atmospheres over moles times Kelvin. Temperature 473 Kelvin. Pressure 2.7 atmospheres. And now we make sure that all of our units cancel. The reason that we do this, part of the reason that we write our units out every single time, all of the time, is to make sure that our units cancel. This problem, all of the units are nice and convenient for us. They will not always be nice and convenient for us. Sometimes we'll have to convert them. If you don't remember to do that, but you write your units out, you'll get to a point, the units canceling part that we're doing now. You'll get to this point and you'll see, oh, my units don't cancel out, I forgot to convert something, and then you can go back and you can fix it. You can convert your units. That's why we're doing this. So moles and moles cancel. Kelvin and Kelvin cancel. Atmospheres and atmospheres cancel. And liters is left. This will also help catch mistakes if you do your algebra wrong. It also requires that you know when things cancel. So maybe this is an instance where you would not be helped. So we multiply everything that's on the top. and we divide by the thing on the bottom. Our volume, our value of volume, is 6.52 after we, nope, 6.5 after we round for two significant figures. Questions at all? Take a short break. All right, coming back from our break, I showed you how to use the ideal gas law, and I'll now give you a chance to use the ideal gas law. So give it a try. PV equals nRT. R equals 0.0821 liters atmospheres per mole Kelvin. All right, so an 8.5 liter tire, 8.5 liters, liters is a unit of volume, so V equals 8.5 liters. An 8.5 liter tire is filled with 0.55 moles of gas. Moles is a unit of amount of gas, or moles. So N equals 0.55 moles. So 0.55 moles of gas at a temperature of 306 Kelvin. So T equals 306 Kelvin. We are asked for the pressure of the gas in the tire. So we're finding P. We need to rearrange PV equals nRT to get P by itself. So we're going to move V to the other side. P equals nRT over V. So plug in 0.55 moles times R, 0.0821 liters atmospheres over moles Kelvin, times T, 306 Kelvin, divided by pressure, divided by volume, 8.5 liters. Our units of moles will cancel. Our units of Kelvin will cancel. Our units of liters will cancel. And we will be left with units of atmospheres. So 0.55 times our ideal gas law constant times 306 divided by 8.5, 1.6 atmospheres. Which would be about 24 psi, just in case you're curious what that is in a more relatable unit. So if it was a tire on most of our vehicles, it's probably a little flat. Need to put a little more air in.
It's not 16?
I don't think it's 16. Did you put in 0.0821 or did you put in 0.821? That would be my guesses. Why it's 16. Any other questions? So that was the easiest case scenario, or one of the easiest case scenarios for the ideal gas law, because we didn't have to convert any units. In this problem, as the header suggests, we have to do some unit conversions. So what volume, what being our question word, volume following it means we're finding volume, is occupied by 3.76 grams of oxygen gas at a pressure of 88.4 kilopascals and a temperature of 19 degrees Celsius. Assume the oxygen is ideal. This is another one of those for the but sort of folks, I might be included in them. Assume the oxygen is ideal, just you can use the ideal gas law. That's all that that's saying. So our ideal gas law is, who knows it? Fortune favors the bald. Ooh, looks like we all have hair. Guess it'll be me then. PV equals nRT. R is what pirates say, and it's 0.0821 liters times atmospheres per mole Kelvin. There's also a version that I think is in millimeters mercury instead of atmospheres. That doesn't really help us here, though. So let's identify some things. Pressure, 88.4 kilopascals. kPa. Our temperature, 19 degrees Celsius. What's our other variable? We're finding volume, we have pressure, we have temperature. What's the other one that we need? We need moles, we need N. So we need moles of gas. Let's start with pressure. Pascals is our SI unit. The kilo means 1,000. So this is equal to 88,400 pascals. We would need to look up a conversion factor between pascals and what unit? Atmospheres. How many pascals are in 1 atmosphere? How many physician's assistants are in 1 atmosphere? Is it on the yellow sheet? It's a big number. It's not 760. Yeah, 101,325 equals 1 atmosphere. So we're dividing 88,400 by 101,325. And we'll get 0.872440168 atmospheres. Put a line under our 2 to remind ourselves this is a number that has 3 significant figures. We don't round it because that could give us a rounding error. So our final answer might be off a little bit if we round it early. What do we do to convert from Celsius to Kelvin? Yeah, add 273.15, and magically it'll turn into Kelvin. So 292.15 Kelvin. And now we need to find the number of moles. We're given grams of oxygen gas, right? So we can start with grams. Can we turn grams into moles? Yes. Yes, we can turn grams into moles. We have to be able to do that to solve the problem. What do we do to convert from grams to moles? What do we do to convert from grams to moles? We use molar mass. Do we multiply or divide? We divide. You're correct. What is the molar mass of oxygen gas? It is not 15.999. Oxygen exists as O2. Horses need oats for clear brown eyes. So there's the trick. I just love reminding us of the fact that some of these gases exist as diatomic molecules. Since it's O2, it's 2 times 15.999 grams per mole. So 31.998. So 3.76 divide, and we get 0.11750734 moles questions. All right, plugging in to solve for V. V equals our number of moles, 0.117 ... moles times 0.0821 latum per molk times temperature 292.15 Kelvin all over pressure 0.872 ... atmospheres. Atmospheres cancel atmospheres. Moles cancels moles. Kelvin cancels Kelvin. Liters is left. And this is where it's really helpful to have a calculator that you can call up the numbers that you've used previously. Like my favorite, the TI-36. Our liters is 3.23. The next number would be a 0, so we round it to 3.23 liters. Questions? Great. Other things that we can do with the ideal gas law is we can find the molar mass of a gas. We can use the ideal gas law along with, I don't know what I meant there, with mass measurements to calculate the molar mass of a gas. For example, a sample of gas has a mass, as all gas does. this gas has a mass of 38.8 milligrams. Its volume is 224 milliliters, temperature of 55 degrees Celsius, pressure of 886 torr. Find the molar mass of the gas. What are the units of molar mass? That's right, you're thinking it, hopefully. Grams over moles. We have milligrams. We can convert that to grams. 0.0388 grams. Great, we've got grams. We would need to take our grams and divide it by a number of moles. Do we have moles? Nope, we don't have moles, but we can find moles. So if we solve our ideal gas law for N equals PV over RT. We have pressure, volume, and temperature. None of them are in the right units, so that's fun. To convert them to the right units, we can do all of these things. So 55 degrees Celsius, add 273.15 for 886 torr. If we divide by 760, that'll convert it into atmospheres. Our 224 milliliters, 0.224 liters. I'm sort of skipping over all the ideal gas law stuff because we've done some examples of that, so it's not really exactly the focus of this slide. All right, so finding our N, our pressure, 886 divided by 760. Our volume is 0.224 liters. R is still the same that it's been. And temperature is 328.15 Kelvin. Kelvin and Kelvin cancel. The liters and atmospheres cancel, and moles flips to the top. The reason that moles flips to the top is it's in the denominator, it's on the bottom. On the bottom, it's kind of like a double negative, but an exponent version actually, and that causes it to flip to the top. So putting all of that into our calculator, we would find a moles value, 0.009736146 moles with 3 sig figs. So now that we've got grams and moles, if we take grams, we divide it by moles, this is the grams of the gas, this is the moles of the gas, that'll give us the grams per mole of the gas. So 0.0388 grams divided by 0.00973 moles. The units just combine to grams over moles. And we get a value of about 3.9 0.9 grams per mole. Any questions on that? There are a couple of indicators, a couple of limiters, things that could cause this to not make sense, or things that could guide us on whether this answer makes sense. What's the lightest element on the periodic table? Hydrogen. What's the mass of hydrogen? The molar mass of hydrogen is about 1 gram per mole. If we got a value that was less than 1 gram per mole, this wouldn't make sense. We could have protons just floating around. I don't think it's likely, but it could possibly happen. If we got a value less than 1 grams per mole, that doesn't make any sense. I think the highest mass of anything we've seen so far in the class is alum, potassium aluminum sulfate dodecahydrate, the KalSO4 12H2O. That was like 474. So if you got a number that was bigger than that, or even close to that, that's really high for a gas. 4 is within our range of 1 to about 500. So that seems somewhat reasonable. The way to make this a fun question is to, instead of asking you what's the molar mass of the gas, to ask you what is the gas? What's the identity of this gas? Any guessers? Yeah, helium. We look at our periodic table, we find helium. Helium is a gas. Helium's got a molar mass of about 4. This is 3.99. That's pretty close to 4. So this is probably helium gas. All right, a sample of gas has a mass of 827 milligrams. Great, it is a different question. Its volume is given, its temperature is given, its pressure is given. Find the molar mass optionally. If you can, I don't remember if you can, identify the gas. I'll give you all the constants that you need. Okay, that should be everything that you need to solve the problem. All right, so some of these variables we are given in units that need converting. Volume is not one of them. Temperature will end up being 361.15 Kelvin. Pressure we divide by 760, 1.28, and some change, atmospheres. We rearrange PV equals nRT to get N equals PV over RT. We have the mass of the gas. We need the moles of the gas to find molar mass. That mass also, if we divide by 1,000, we'll get grams, so 0.827 grams, just below the red line. So N equals 1.28 ... atmospheres times volume, 0.270 liters over R. and T. Our units cancel out to leave us with moles. Our moles are 0.0116 dot dot dot. We need to use the whole thing. The dot 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 just means that there's other things. I didn't write them. I know that they're there. I'm using them. You can also do this to signal to me. You know that there's more things and you're using them. Just make sure that you do actually use them. Then we take our grams, divide it by our moles. We get units of grams per mole. Let's find out what that number is. The number is 70.7 after we round for 3 significant figures. Grams per mole. This would be a harder version of the previous problem if I decided to make it fun and ask you what the identity of the gas is. You might be thinking, oh, it's gallium, or it's germanium, it's Ga or Ge. Maybe, unlikely. Those wouldn't be gases at this temperature. What would be a gas at this temperature is chlorine. Horses need oats for clear brown eyes, Cl for clear, clear for Cl for chlorine. Chlorine exists as diatomic, which would be Cl2, 35.45 times 2, 70.90. It's pretty close. So that would be my best guess for what this gas is, or your best guess, maybe. Again, that's just the extra added, in my opinion, fun add-on to this question. Any questions about the other parts? All right. Other things that we can do with kinetic molecular theory is have mixtures of gases. Oftentimes, you're not going to have just one pure gas. Most of the time, you're not going to have just one pure gas. According to kinetic molecular theory, each of the components acts independently of the others. So any gas behaves the same as any other gas. That's an assumption that we're making. It's not true, but it's true enough that we can get away with it for the ideal gas law. What this means is that the pressure from any individual component, which is called the partial pressure, adds to the total pressure. Pressures of the individual gases add up. To the total pressure. Because we're making the assumption that they don't interact with each other, if they did interact with each other, then the pressure might be higher or lower than we would expect. They don't do that, and so they just add up nicely linearly. This is sort of like if we have a mixture of a bunch of liquids that don't mix. So let's say we've got a test tube, or better yet, we've got a graduated cylinder. And we've got in this cylinder green liquid. We've got some red liquid. We even have some blue liquid. If these don't mix at all, if they don't interact, if we add up the volumes of each of the liquids, then we'll get the total volume of the liquid. What we're doing with pressure is similar. So adding up the pressure, if we know the pressure of the individual components, we can add them up and that will equal the total pressure. We can also find the partial pressure, the pressure of one component. We can find the pressure of one gas in a mixture from the total pressure. We need to know the fractional composition, so what percent but turned into a decimal. So percent but in decimal form. We need to know what fraction of the gas mixture is that one gas, and we can get the partial pressure. I'll show us what that looks like at some point. This point. The air in our atmosphere is a mixture. It's mostly nitrogen. There's also some oxygen, argon, carbon dioxide, and some other smaller gases. The nitrogen molecules exert a certain pressure that contributes 78% of the total pressure. Let's say that we're at high elevation and the pressure is 0.778 atmospheres. I have no clue what elevation this would be at. Maybe it's not possible unless you're in a plane. Who knows? If the total pressure is 0.778 atmospheres, the total pressure we often indicate P sub TOT, TOT standing for total. So that pressure around us is 0.778 atmospheres. If we know that the air is 78% nitrogen, this is 0.78 as a decimal. This would be the fractional composition. That's what we called it on the previous slide. So the fractional composition is 0.778. The partial pressure of nitrogen, P sub N2, because nitrogen is diatomic, is the fractional composition. This would be represented as chi N2. It looks like an X, but it's got a little thing on the front that lets us know that it's the Greek letter chi, times the total pressure, 0.778 atmospheres. This would be P TOT. So at this elevation, the partial pressure of nitrogen gas, 0.61 atmospheres. So this is the pressure of just the N2. For the case of N2, this isn't particularly important. If we did it for O2, though, our bodies need oxygen to live. If the partial pressure of oxygen gets too low, we can no longer survive. That's what happens for most people when you go up to elevations like at the peak of Everest. If you go up to the peak of Everest and your body's not adapted to very low oxygen levels, you need oxygen cylinders so that you can supplement the oxygen that's in the air. The partial pressure of oxygen is too low for you to breathe. All of the gases in the mixture add up to the total pressure. The optimist says the glass is half full. The pessimist says the glass is half empty. The chemist says the glass is full. It contains 50% H2O as a liquid, 39% N2 as a gas, 10.5% O2 as a gas, and so on and so on. The glass is full. Anyways, there's a meme for you. It's an old meme, but it works. An example with partial pressures. a gas mixture contains 64% methane, 36% ethane. If the total pressure is 1.44 atmospheres, what are the partial pressures? Our formula is that we'll call it P sub A equals chi sub A times P sub TOT. So P sub A is pressure of A, chi sub A is the fractional composition of A. Remember that fractional composition is just percent turned into a decimal, so percent divided by 100. Whoa, divided by 100. P sub TOT, total pressure. The easy way to get the fractional compositions is just scoot your decimal place 2 to the left. So the pressure of methane, P sub ME, 0.64. The pressure of ethane, P sub ET, 0.36. P total, we're given, it's 1.44 atmospheres. Questions at all? Then we just plug things into our formula. So the P, sorry, those are not P and P sub ME, it's chi sub ME, my bad. We're finding partial pressures. So P sub ME equals 0.64 times 1.44. P sub ET equals 0.36 times 1.44 atmospheres. So 0.64 times 1.44, the pressure of methane, 0.92 atmospheres. The pressure of ethane, 0.52 atmospheres. This is what I would consider a boring partial pressures question, but you will also get mad at me if I give you fun partial pressures questions. So I probably won't. I don't think I usually put fun partial pressures questions on the exams. If I do, it would be 1. All right. Another part of partial pressures is the pressures add up to the total. So Dalton came up with this law. This is Dalton's law of partial pressures. This works for ideal gases. We're assuming that our gases are ideal. So the sum of the partial pressures of each component must equal the total pressure. This is what I was talking about with the analogy with the volumes. If the volumes add up, right, if we add up all the volumes, that's the total volume. And that works if the liquids don't interact. Sometimes liquids mix and it would actually be less than the total volume. That's also, the analogy works also for gases. Sometimes the pressures don't add up to exactly the total pressure. In our class, they do, because they're ideal. They're not real. It's not fun. It's not as fun to work with real gases. they work differently. This is generally true with a little margin of error. So the total pressure is equal to the pressure of component A plus the pressure of component B plus the pressure of component C, and so on and so forth. However many things you have. Usually we'll have like 2 or 3. So let's say that we've got a sample of hydrogen gas mixed with water vapor. Our 2 components, we only have 2 components, hydrogen gas, water vapor. The mixture has a total pressure of 734 torr. So let's label P sub TOT equals 734 torr. The water vapor has a partial pressure of 22.5 torr. So P sub H2O, that's the partial pressure of water, equals 22.5 torr. What is the partial pressure of the hydrogen gas? So we need to adapt Dalton's law of partial pressures for hydrogen gas and water vapor. Those are the only 2 things that we have in this mixture. So Dalton's law of partial pressures says the total pressure is equal to the partial pressure of both of the components. In this case, just 2 components. So P sub H2O plus P sub H2. Not in that order, in this case. We have P total. We have P sub H2O. So 734 torr equals pH2 plus 22.5 torr. Rearrange. We've got 734 torr minus 22.5 torr. If you accidentally added them, you'd get a pressure that's bigger than your total pressure, and that should set off some little alarm bells. Our partial pressures will always be smaller than our total pressure. 734 minus 22.5. The pressure of the hydrogen gas is 711.5 torr. We'll call that 712 when we round. We will be doing this exact thing in one of our labs, experiment 9, I believe it is. Questions about this partial pressure problem? Okay. Our lungs perform well at an oxygen partial pressure of 0.21 atmospheres. That's 1 atmosphere total pressure when P sub O2 is, when chi sub O2 equals 0.21, 21%. That's what oxygen normally is. Oxygen's about 21% of our atmosphere. This is basically just saying we do well when we're at sea level. Our lungs function well at that elevation. If you go up to higher elevations, you run out of breath sooner because there's less oxygen in the air. The total pressure is decreased. The fractional composition has remained the same. The partial pressure of oxygen, therefore, has decreased. If you get to extreme heights, then you can suffer from hypoxia. If the pressure is less than 0.1 atmosphere for PO2, severe hypoxia can result in fatality. People who summit Everest typically bring oxygen with them to try to avoid that. On the other hand, you can also have oxygen toxicity. So there is such a thing as too much of a good thing. Oxygen's mostly a good thing. Having too much of it can be problematic. So if you get too much oxygen, pressures of greater than 1.4 atmospheres, so you'd have to be at elevated pressure to experience this, then you might get twitching, tunnel vision, convulsions. And that's the sort of thing that might happen if you're scuba diving and your heliox mixture is not set properly, or other things like that. Part of the reason that scuba diving is dangerous and you need to do training to be able to scuba. Pressurized air also has an increased partial pressure of nitrogen, which can give you nitrogen narcosis, or what I think is more fun, rapture of the deep. Rapture of the deep apparently is similar to being tipsy. I've never gone scuba diving. I haven't experienced nitrogen narcosis. I'm guessing it's not fun. If you go deep sea diving, if you're below 50 meters, that's when you'd use a specialized mixture like heliox. So it's just helium and oxygen, and that helps you avoid nitrogen narcosis because you take nitrogen out of the picture. Helium, being a noble gas, very safe to breathe. Doesn't react with your body. The example that we looked at previously, the last example that we looked at, is this scenario. So we've got gas that we'd collect into a beaker of water. So flip a piece of glass upside down, make sure that it's completely full of water, and then you can trickle bubbles up or create bubbles, and they'll catch at the top. So in this picture, we're piping some bubbles in, it's filling up. And eventually that thing could get completely filled up. We'll be doing this, but we'll be generating hydrogen gas by dissolving magnesium metal in acid. That'll produce hydrogen gas. We'll collect all the hydrogen gas. We'll figure out how much hydrogen gas we've produced. We'll do some partial pressure stuff. And then we can figure out the moles of hydrogen gas that we've collected. The pressure of the water vapor in the mixture, because water vapor will also be in here, so gas plus H2O as a gas. It's just going to be those two things in there. The pressure of the water vapor depends on temperature. And you would just look up in a table what the partial pressure of the water would be. In an example like this. So let's say that hydrogen gas is collected over water. So we've got hydrogen gas, we've got water. We have a total pressure of 758 millimeters mercury and a temperature of 25 degrees Celsius. We want to find partial pressure of the hydrogen gas. What are the components in our beaker, in our piece of glass? What are the gas components in there? Two of them. Ideas? H2O and what? What gas? We've got H2O vapor, and what's our other thing? What's the other chemical that's mentioned in the problem? Hydrogen. Yeah, we have H2 gas. The horses of horses need oats for clear brown eyes. We are trying to find partial pressure of hydrogen. P sub H2. We have total pressure. What do we need to be able to find the partial pressure of hydrogen gas? If we've only got those two gases, how do their pressures relate? Do they add up? Do they subtract? Do they divide? Do they multiply? Or are they not related at all? I'm just going to assume that our brains are fried because it's late in the day. They add up. So we need to find the pressure of the water vapor. It's a Dalton's partial pressures law. So we take this 25 degrees Celsius and we find the matching temperature in our table. The table tells us that the vapor pressure of the water is 23.76 millimeters mercury. So 758 mmHg equals 23.76 mmHg plus whatever the pressure of H2 is. So skipping the algebra step, 758 minus 23.76, the pressure of hydrogen gas is 734 mmHg. We will be doing this in a lab. Questions? We're almost there. Almost done. We can also use stoichiometry. So if you thought we were done with stoichiometry, you were wrong. We're using it again. In reactions involving gas reactants and products, the amount of gas is often specified in terms of its volume at a given temperature and pressure. Those are three things that we can measure with relative ease. Volume, pressure, temperature, V, T, P. We can use the ideal gas law, PV equals nRT, to convert pressure, volume, and temperature to moles. So finding N. We've seen this before. We used it for our molar mass problems. PV over RT is equal to N. So we can find the moles of the gases. Then we can use the ratio from the balanced chemical equation to convert to other quantities. Let's take a look at what that might look like. Sulfuric acid is the industrial chemical produced in the greatest quantity in the United States and maybe in the world. It's prepared by the overall chemical equation as follows. This is a balanced chemical equation because it has coefficients, so we don't need to worry about balancing it. Our question is, what volume of O2 in liters at 22 degrees Celsius, 745 millimeters mercury, is required to produce 907.18 kilograms of sulfuric acid? The way that this question is worded, some of you will be trying to find, some of you will incorrectly identify that we're trying to find something about H2SO4. We are not trying to find something about H2SO4. Volume of O2 is right next to our question word. That is what we are trying to find. So we are trying to go from stuff about H2SO4 to O2. Liters of O2, volume of O2. we are given 907.18 kilograms H2SO4. We can convert that to grams. Of H2SO4. We can convert that to what? What can we convert grams to? Moles. We can convert to moles. We need the molar mass of H2SO4. Which is 98. So dividing by 98.078 grams per mole. It's a lot of moles, many moles. 9249.5 ... moles H2SO4. The reason that we are finding moles of H2SO4 is we're trying to find liters of O2 using our ideal gas law, PV equals nRT. We're trying to find V. V equals nRT over P. We were given pressure, we were given temperature, R is a constant, N is something that we don't have. We don't have the number of moles of oxygen, so we can't calculate the liters, the volume of oxygen. But we can calculate the moles of sulfuric acid. We can convert the moles of sulfuric acid to moles of O2. The two things that we care about, the sulfuric acid, the oxygen, pull those out from our balanced chemical equation to make our conversion factor. So we get out 2 sulfuric acids, 2 H2SO4 for every 3 O2 that we put in. This lets us convert to moles of O2. So times 3 divided by 2, the number of moles of O2, 1,387 for 0.3 ... moles O2. Normally our numbers won't be this big, but this is like the amount that the world produces in a year, so it's a big number. Then we can plug that in to this nRT over P. T is 295.15 Kelvin. In atmospheres, the pressure is 0.9802 ... atmospheres. We're going to end up with an absurd number of liters. We're going to end up with 342,970 liters, which would round to 343,000, and we'll just call it kiloliters. There's 2 more slides. Then we're done. Then you're free for the weekend. There's a set of conditions that we call standard. The conditions are temperature and pressure. Standard temperature and pressure is STP. STP is 0 degrees Celsius and 1 atmosphere. What is 0 degrees Celsius? What's special about that number? That's right. It's the freezing point of water. Where is the pressure 1 atmosphere? Huh? Sea level. At the beach. Because the beach, assuming it's not Reedley Beach, is at sea level, right? So if we're at the ocean, so STP, freezing cold, but at least we're at the ocean. Could be worse. STP, freezing cold, 1 atmosphere. 0 degrees Celsius, 1 atmosphere. They're also really easy numbers, 0 C, 1 atmosphere, 0 and 1. The volume of 1 mole of gas at STP V equals nRT over P for 1 mole, 0.0821 liters atmospheres per mole Kelvin. You don't need to worry about doing this. The result is already given below. Times 273 Kelvin over 1 atmosphere. Atmosphere is moles, moles, Kelvin, Kelvin, atmosphere is Kelvin. All the units except for liters cancel. And it's about 22.4 liters. 1 mole of an ideal gas at 0 degrees Celsius and 1 atmosphere is 22.4 liters. Part of the reason that I show you the conversion, or I show you how we got this 22.4 liters, is because you might not remember this 22.4 liters per mole. There's going to be probably problems with that. If you remember STP, that it's 0 degrees Celsius and it's 1 atmosphere, you can get the 22.4 liters for 1 mole. Here's an example of a problem where we can use that liters per mole term. We can only use it if we're at STP. If you're near STP, you can still use it as an estimate, but you should know that you're going to be wrong by a little bit. So we want liters of nitrogen to form 9.85 grams of NH3. 9.85 grams NH3. We can convert from grams to moles using molar mass. Our molar mass is 17.031 grams per mole. This will give us moles of NH3. A decent first instinct to have anytime you see grams is maybe we need to convert it to moles. This is 0.578 and change moles NH3. What is the chemical that we are trying to find? Nitrogen. Nitrogen being N2. So the two things we care about, ammonia and nitrogen, we can convert to the amount of nitrogen. The 2 NH3 goes on the bottom, the N2 goes on the top. So we divide by 2. 0.2891 ... moles of N2. And here's where that molar volume at STP comes in handy. 22.4 liters per mole. This is if we're at STP. We want liters of nitrogen. We have moles. We have a conversion factor between liters and moles. So times 22.4 liters per mole. The moles cancel. We get a volume of 6.48 liters of N2. You can also use this at any conditions that you're reasonably going to be in. You can use that 22.4 liters per mole just as like a guesstimate number to calculate the volume of various gases, or the number of moles of gases if you have the volume. Any questions at all about gases? And we will stop there.